Hello and welcome to the second week of learning in Unit 3. So just as a reminder, Unit 3 is called Chemistry and Society and it's got these topics that you can see on the screen. Metals we're going to leave till the end. We've looked at plastics last week and this week we're going to look at fertilizers. We're going to begin with a couple of starter questions to recap the plastics topic. Okay, so first one, the structure of the methyl methacrylate monomer is shown. And you have to draw a section of the polymethyl methacrylate polymer showing 3 monomer units linked to joined together, and you also have to name the type of polymerization taking place. So pause the video now and make sure you attempt that question. Okay, so here are the answers here. So to draw the polymer with 3 monomer units linked together, you just have to remember to draw 3 of the units beside each other. The double bonds break, so there should be no double bonds in the structure, and all of the carbon atoms, the 6 carbon atoms that were a part of the double bonds, will link together. So remember that if you're showing the polymer unit, you show these free bonds at the end, and then single bonds connecting up all of the atoms together, and it is addition polymerization because each monomer adds on to the next one by breaking the double bond, a little bit like an addition reaction which also breaks the double bond. Okay, question 2. This one's a bit more difficult. I've put this one in just to give you a bit of practice, but I'm going to explain it over the next couple slides. So a copolymer is formed when 2 different monomers polymerize. Part of the structure of a copolymer, showing 3 monomer units, is given below. One of the monomers used is propene, and you have to identify the other monomers. You've got 4 options here: pent-2-ene, pent-1-ene, but-2-ene, and but-1-ene. So if you want to, pause the video now and give this question a go. If you're finding it a little bit tricky, if you're thinking I don't know where to start with this, I'm going to go over it in the next slide. Okay, so with this question, this is a sort of problem-solving question. You've not learned about copolymers, but it's kind of explaining what it is. So it's one with 2 different monomers. So the first hint for sort of figuring out what monomers a polymer structure is made of is finding the H shapes. So what I've done is so there's our H here, and I've circled the different H shapes in this structure. We're going to assume that this is 3 different monomers linked together. So if we look at these H shapes, each one would represent a monomer. The first and end ones have 4 carbons, and the middle one has 3 carbons. So this middle one has 1, 2, 3 carbons. So the middle one must be the propene, and it says one of the monomer used is propene. But we have to identify the other one. So the first one, this one here, and the end one here have 1, 2, 3, 4 carbons, so they must be butene. So straight away we can rule out A and we can rule out B, and then we've got to think, well, is it but-1-ene or but-2-ene? And then you've just got to think about the fact that if you've got a polymer chain here and it's made up of these H shapes all connected together, the bar, if you like, the middle bit of the H would be where the double bond was. So you can think of this as being coming from the monomer that looks like this with the double bond in the middle. So then we just have to find the longest chain of carbon atoms, 1, 2, 3, 4, or 1, 2, 3, 4, it doesn't matter. Either way, the double bond is between carbon number 2 and 3, so we would call it but-2-ene. So that's the answer to that one. Okay. Right, so we're going to be looking at fertilizers. As usual, I've got some slides where it's background information you don't need to write down, and then I've got some slides where it's key knowledge that you do need to write down to help you to remember it. So I've got some learning intentions. If you want to, you can pause the video now and have a read through. There are quite a lot though, so it's maybe better just coming to these at the end. Okay, so we're learning about fertilizers. The summary is we're learning about fertilizers and we're learning about the processes by which chemists can make fertilizers. So Haber Process and the Ostwald Process, and we'll start by looking at what a fertilizer actually is. You might have some idea of that already. Okay, in fact, before we start looking at fertilizers, we've got a little slide here about the importance of plants. So hopefully you're aware of this, but I think it's important to emphasise all of our food comes either directly or indirectly from plants. Whether you eat meat or not, eating meat is still coming from an animal which has at some point eaten a plant. So without plants, there would be no us. And plants are able to photosynthesize, meaning they can make carbohydrates from water, so they can take in water through their roots, carbon dioxide from the air, and using the sun for energy, they can turn these raw materials into carbohydrates and proteins and other things as well. So as well as taking in carbon dioxide and water, plants also need a range of other elements, and they take these up through their roots from the soil. So some of the plants need a lot of different key nutrients, but probably the kind of main ones that they need in quite good quantities to grow well are nitrogen, phosphorus and potassium. So I mentioned that as well as carbohydrates, plants can make proteins. They need nitrogen in order to make proteins. Proteins contain nitrogen. Phosphorus is an important element in DNA, so plants need that for their cells to be able to grow and reproduce. And potassium, I'm not exactly sure of the role of potassium. I think it's involved in producing flowers. So plants are really important, and they must be able to get all of these nutrients from the ground. Now, normally, when we've got wild land, we have a kind of cycle of growth and decay. And what that means is that when a plant uses nutrients up from the soil, they will get depleted, they'll become less a little bit, but then when the plant dies, the bacteria in the soil will break this plant back down into all of its sort of original components, and all of those nutrients will be recycled. And so we've got this cycle here. But when we harvest crops, when we farm farmland, the crops are taking up these nutrients, but then we're removing them from the soil, so those nutrients are not getting recycled back into the soil, and so the soil can become depleted in nutrients in farmlands. And that's why when you're farming or gardening or whatever it is that you're doing, you often need to add fertiliser. So I'm just going to talk a little bit about nitrogen specifically. So I mentioned that nitrogen, phosphorus and potassium are some of the key nutrients, and we've mentioned that the nutrients are generally cycled. So I'm going to just talk about nitrogen. So you might remember, you might have known that most of the atmosphere is nitrogen. About 80% of the atmosphere is nitrogen. So you might think, well, why can't plants just absorb nitrogen from the atmosphere like they do with carbon dioxide? Well, nitrogen is quite different to carbon dioxide in its chemistry. Nitrogen has a very strong triple bond in this N2 molecule, and therefore nitrogen is very difficult. The nitrogen molecule N2 is very difficult to break apart. It's very unreactive, and it's very difficult for plants to access that. So plants can't just absorb nitrogen from the air, and they have to get it in other ways. So one way in which nitrogen is created into an accessible form for plants is actually through lightning. So lightning reacts the nitrogen and oxygen in the air because of the extremely high temperatures, and that allows some nitrogen to reach the soil. Another major way in which nitrogen can reach the soil is through special nitrogen, what we call nitrogen fixing bacteria, which live in the root nodules of legume plants. So legumes are things like peas, beans, clover is also an example of a legume, lentils, all those types of plants have a symbiotic relationship with nitrogen fixing bacteria, and those bacteria can carry out the chemical reactions necessary to get nitrogen from the atmosphere into what we would call a biologically available form. So nitrogen is one of the, because it's a component of proteins, it's needed in quite large quantities by plants, so it's one of the more important ones. So nitrogen content in agricultural soil can be increased in a few different ways. First one is just something called crop rotation. So if you are harvesting the same field again and again without putting any more nitrogen in it, the nitrogen in the soil will get depleted. But if you include some of these plants which can do nitrogen fixing, then you will be able to replenish some of the nitrogen in the soil. Another method is to use natural fertilizers. So animal manure as well as composted plant material would be considered a natural fertiliser. So you'll probably see this in Dumfries and Galloway quite frequently if you see farmers spreading slurry, etc. on the fields, or if you have a garden at home you might put compost in there. And then the final way is to add synthetic fertilisers. So synthetic fertilisers are fertilisers made by the chemical industry. I'm quite conscious I haven't actually given a definition of fertilisers yet, but I think we've got it on the next slide. Okay, so this is a kind of summary of what you need to know about fertilisers. So we need to know that growing plants requires nutrients, and this is our definition. So fertilisers are substances which restore elements essential for plant growth to the soil. Most fertilisers contain nitrogen, phosphorus and potassium. So you'll see the symbols here, NPK. If you're buying an artificial synthetic fertiliser, you'll usually see the symbols NPK, and quite often it gives you the composition, what proportion of the fertiliser is nitrogen, phosphorus and potassium. So we mentioned that plants take up most of their nutrients through the water that they absorb, so for that reason fertilisers must be soluble so that they can be absorbed along with water through the plant's roots. So make sure you write down the information on this slide. Okay, so bearing in mind the information we've just learned, you're going to do a little chemistry task now and identify the compounds here which could be used as suitable fertilisers. So you've got lots of different compounds and you need to remember that they have to have the correct nutrients, so either nitrogen, phosphorus or potassium. They don't have to have all three in one compound, but they need to have one of those, and they also need to be soluble in water. So you're going to need to check the solubility using your data booklet. Okay, so it's page 8 of the data booklet that you need to have a look at, and it's got this solubility table on it. So you'll need to look at each compound. If it's NH4, that means it's ammonium. So you're going to look down the table for ammonium, then you're going to look along for chloride in the table on page 8, and you will see for this first one, ammonium chloride is very soluble. It contains nitrogen, so it can be used as a fertiliser. So there's this one can be, and then there are 7 others. Write them down and make sure you pause the video and do that before checking your answers on the next slide. Okay, so here we go. That's the 7 compounds that are soluble and contain either nitrogen, phosphorus or potassium, so they can be used as fertilisers. So this isn't mandatory knowledge at National 5, it is mandatory at National 4, but it's important background knowledge. So fertilisers, both natural and man-made fertilisers or synthetic fertilisers can cause problems, and the main problem caused by fertilisers is this issue of what we call eutrophication. So when you spray a fertiliser on a field, whether that's manure like slurry or whether that's a synthetic fertiliser, some of it probably through rain will end up washing into a lake or a river. This can be minimised by spreading the fertiliser when there's not likely to be any heavy rain. If you spread fertiliser just before heavy rain, it can cause really big problems. But even if there's just a little bit of rain, that will still wash some of the fertiliser away. And the fertiliser will then fertilise algae in the water system, in the lake or river. It will fertilise the plants in the river as well. And you might think, okay, well that's a good thing surely. And perhaps it is for the algae, but what happens is that when all these plants and algae grow, there's what we call a big algal bloom, and the algae die, and some of the plants that they've maybe shaded out die as well, and then all this dead algae and plants have to be decomposed by microbes, and the process of decomposing all that dead algae uses up oxygen in the river. That means that the dissolved oxygen levels in the river or lake fall, and leads to fish suffocating and other aquatic organisms suffocating and dying. So fertilising lakes and rivers is not actually a good thing, and it can cause quite severe problems. Okay, so we're going to move on now and we're going to look at the different ways of making fertilisers. So from the summary, you need to know what a fertiliser is, and so it's a substance that restores nutrients to the soil, and we're going to look in this next section at how synthetic or man-made fertilisers are produced, because that's what we make in the chemical industry. So if you were employed as a chemist making fertilisers, you're going to be making synthetic or man-made ones. And the two processes that we use for making fertilisers in the chemical industry are the Haber process, which makes ammonia. So ammonia, you can see ammonia contains nitrogen here. Ammonia is, making ammonia is the main way in which we can get nitrogen out of the air and turn it into a usable form. So this is an extremely important process, the Haber process. And then we've also got something called the Ostwald process, which makes nitric acid. So again, it's a nitrogen containing compound. Nitrogen is a key nutrient for plants. So we're going to look at how we make these two chemicals, ammonia and nitric acid, and then we're going to look at how fertilisers are produced from these starting materials in neutralisation reactions. So we get these two starting materials and then we use them in neutralisation reactions to produce soluble nitrogen containing salts, which can be used as fertilisers. We wouldn't just put acid straight on to the crops, it wouldn't go down so well. So we're going to start with the Haber process, and rather than me explaining it, I would like you to watch a couple of quick little videos which will talk you through the Haber process. They're nice and quick. I'm going to put a link to these. I think you might be able to watch them straight from the video, but I'm going to put a link in the description. So make sure you watch these before you move on. Okay. So this slide is just a little summary of what you should have seen in the videos. So the Haber process takes nitrogen and hydrogen from the air and reacts them together. And you've got special conditions for the reaction. So you need to remember that the Haber process uses an iron catalyst, and you need to remember that it uses an intermediate temperature. So if the temperature is too low, the reaction is too slow and not very profitable. But if it's too hot, then this ammonia can break back down into nitrogen and hydrogen. You should have seen that in the videos that you've watched already. So we're going to write down a sort of simplified summary of this on the next slide. Okay, so hopefully this is a little bit simpler for you to write down than the previous slide. So we've got the Haber process here. Nitrogen and hydrogen from nitrogen from the air and hydrogen, which mainly comes from natural gas, react together to produce ammonia. Something that's worth noting, adding to your notes on here, is just, if you didn't already remember this, this arrow, this two-way arrow here, means that this is a reversible reaction. So you should have already seen the videos on the Haber process, so I'd just like you to make sure you pause the video now and take a note of this key information. This comes up all the time in tests and exams. Okay, so I'd asked you to balance the equation, and that's the answer just there. Okay, we're now going to move on to the Ostwald process, and again, rather than me talking through this, I've got a video that I'd like you to watch, and I'll put the link in the description of this video that you're watching just now. I'll also put it on the team as well. Okay, so hopefully you've already watched that video. If you haven't, make sure you pause it now and pause this one now and go and watch the description of the Ostwald process. So the Ostwald process is used to make nitric acid, and it makes nitric acid from ammonia, oxygen and water. You only need to really remember a couple of key facts about the Ostwald process and write this down. So you really need to know the starting materials, ammonia, oxygen and water, and you need to know the product of the Ostwald process. The final thing you need to know is the catalyst. So remember that the Ostwald process is a platinum catalyst, whereas the Haber process was an iron catalyst. So this can come up in multiple choice questions quite a bit. And you should remember that the ammonia used in the Ostwald process comes from the Haber process. So without the Haber process to make the ammonia, there wouldn't be an Ostwald process to make the nitric acid. So make sure you've written this slide down. Okay, so we've looked at how we can produce ammonia and nitric acid, which are two key nitrogen containing compounds. which are used to restore nitrogen to the soil in fertilizers. But how do we take these and make them into something that's usable? Because nitric acid is an acid; it's quite nasty. Ammonia is a smelly, colourless gas. If you recognise the bad smell, to be honest, associated with like toilets, like urine, that is often a smell associated with ammonia. It's really pungent. It's disgusting. So we can't just take ammonia and put it straight on the fields. It wouldn't work. So what we do is we use neutralisation reactions to react the ammonia and the nitric acid either with each other or with other things to produce soluble salts which can be used as fertilisers. So if you need to know about ammonia, you need to remember that it's a smelly, colourless gas and it dissolves in water to produce an alkaline solution. Sorry, there's a wee typo on the slide there. So ammonia plus water, we've got NH3 and H2O here, and what happens when ammonia reacts with water is that one of the hydrogen atoms, if you like, from the water joins on, but really what's happening is, remember, water can split into an H plus and an OH minus ion, so the H plus ion from water is adding on to the ammonia, the NH3, to give NH4, and it's actually NH4 plus. So ammonium hydroxide, if you look at them in the table on page 8 of the data book, you'll see that ammonium is NH4 plus. I should have put the charges in here. And the hydroxide is OH minus. So that's why this is an alkaline solution, because when we react ammonia with water, we're getting an excess of OH minus hydroxide ions produced. If you want to, you can write out the formula for ammonium hydroxide beside this in your notes, just showing the charges. So it would be NH4 plus OH minus. So once we've got this ammonia solution, so we call it ammonia solution, but it's really a solution of ammonium hydroxide, and this ammonium hydroxide reacts with acids to produce ammonium salts. So if you remember, like hydrochloric acid produces chloride salts, or if you've got a base like sodium hydroxide, the salt name would start with sodium. If we've got an ammonia solution, it's going to produce salts which start with ammonium. So ammonium hydroxide plus nitric acid, the first part of the name of the salt is going to come from the base, or the alkali, which in this case is ammonium hydroxide. So the salt's going to be named ammonium, and the second part of the salt name comes from the acid. So if it's nitric acid, it's going to be ammonium nitrate plus water. So what I'd like you to do now is see if you can complete the word and symbol equations that I've got written here. So the first one is just completing the symbol equation for this one. Ammonium hydroxide plus nitric acid makes ammonium nitrate and water. And then the second one, you've got to complete the word equation first and then do the symbol equation. So we're looking at ammonium hydroxide reacting with phosphoric acid in this next one. As a wee hint, I'd like you to make sure you look at the acids and bases section if you can't remember the formulas for things like nitric acid, and also use page 8 of the data book, because we've got a lot of compounds here which are what we call contain what we call group ions. So nitrate is one of these group ions. If it ends in 8, it's on page 8, but ammonium and hydroxide are also these group ions on page 8 as well. Final thing, I've spent quite a lot of time on this slide, but the final thing I want to say is just talking about state symbols. So I've put state symbols in these equations. I'd like you to try and continue that. So remember, we're talking about ammonia solution on this slide, so that's why I've put AQ as the state symbol for ammonium hydroxide. Our acids are always going to be a solution in water. So for phosphoric acid, I've given you the formula here and I've put AQ. So nitric acid as well is going to be an aqueous solution. We never use the pure acid. And because these two things are both solutions, your salts, so your ammonium nitrate and whatever you name the salt here, hopefully you can figure that out, those are also going to be in solution, AQ. And then your water that's produced in this neutralisation reaction will be a liquid. So make sure you use the correct state symbols. Okay, I've talked about this quite a bit. Pause the video if you haven't done so already, and try to do those questions. Okay, right, moving on then. So I've written this out using just the ordinary formulas. I've also used the ionic formulas just in case you've done it that way. Try and stick with either one or the other, so try not to use a mixture of ionic and non-ionic formulas. The exception to that obviously is if we've got a covalent substance like water, then we're not going to give it any charges because it's just covalent. There are no ions in water, although there are. Bad example anyway. So you can see here I've written out the charges on ammonium hydroxide. So you've got NH4 plus OH minus, that's your ammonium hydroxide, and your nitric acid, ammonium nitrate, and water. So I'll let you mark your answers. Okay, I've also I think this top one's already balanced, and I've also balanced this equation. I didn't ask you to do that, but if you haven't done that, then it might be worth adding it in for phosphoric acid. So when we've got phosphoric acid, because each mole, if you like, of phosphoric acid, or each unit of phosphoric acid has 3 hydrogen ions, 3 H plus ions, we need 3 lots of ammonium hydroxide to react with 1 lot of phosphoric acid. So the mole ratio would be 3 to 1 for ammonium hydroxide to phosphoric acid, and then we're producing 3 moles of a oh no, we're not, I've balanced that equation wrong. I should take that 3 out of there, so you're going to have to cross that 3 out if you've added that in. We would only produce 1 mole of ammonium phosphate. That's wrong, because there are 3 of these here, but we would produce 3 moles of water, so please ignore that 3 or take that out there. I've balanced that equation wrong. How embarrassing. Okay, right, a couple more equations in, because we've looked at reactions of ammonia or ammonium hydroxide in neutralization reactions, but nitric acid can also react with bases to produce salts. So we've got 2 examples: nitric acid plus potassium carbonate, just a nice simple neutralization reaction of an acid with a metal carbonate, and that produces a salt called potassium nitrate. So remember, the first part of the name comes from the base, the second part comes from the acid, plus water, and then there's another product. Hopefully you can remember that and fill that in. And I've got another example for you to fill in as well. So nitric acid plus sodium hydroxide, and see if you can remember that just the word equations for these ones is fine. So pause the video now and try and answer those. Okay, so here are your answers here. So the extra product, if we've got a metal carbonate, is going to be carbon dioxide, and then if we've got nitric acid plus sodium hydroxide, we're going to make sodium nitrate and water. No carbon dioxide this time because this is not a carbonate. Okay, a little quick question, you don't necessarily need to write this one down, but which do you think would be a more useful fertiliser? Potassium, oh, hopefully you didn't see that. The potassium nitrate or sodium nitrate? Maybe you spotted that answer when it came up there. So the answer to this one is potassium nitrate is a slightly more useful fertiliser, because both potassium and nitrogen are these essential elements for plant growth. So you need to remember NPK. This comes up quite a bit in questions, just spotting substances which contain these 3 key nutrients for plant growth. Plants probably do need a bit of sodium, to be honest, but sodium is a much more common element than potassium, so there's probably a bit of sodium already in the soil. It's not one that we need to replenish, but nitrogen, phosphorus and potassium are the key ones that we need to replenish using fertilisers. Okay, so thank you for listening. There's been quite a lot in this lesson today. If you think you need more practice, head to the Scholar pages and test, or look at this topic on BBC Bitesize. Please make sure you do this if you're still feeling a bit unsure after watching this video. I'm just going to go back to the learning outcomes and just go through a little summary of what you should know at this stage. Okay, so these were our learning intentions for fertilisers, so it's worth taking a little bit of time just now and seeing if you understand all of these things. So you should be able to state 3 key elements for plant growth. Okay, NPK, so you need to remember that. And you should be able to explain what a fertiliser is and why it needs to be soluble. You should be able to state the reactants and products in the Haber process and the catalyst used in the Haber process. See if you can remember that. Okay, so it's an iron catalyst, and nitrogen and hydrogen are the reactants, and they are used to make ammonia. You should be able to explain why a moderately high temperature and pressure is used in the Haber process. Now actually we didn't cover pressure, I'll need to take that one out. So the moderately high temperature is used because if the temperature is too low, the reaction rate is too slow, but if the temperature is too high, the ammonia breaks down. So sorry about that wee mistake there. And then you should also be able to describe the properties and reactions of ammonia. So that was something that we covered just at the end there, when we looked at, I described the smell of ammonia, and I described how it reacts with water and how a solution of ammonia or ammonium hydroxide can react in neutralization reactions. And then you also need to be able to state the reactants, products and catalysts used in the Ostwald process. So see if you can remember those. And you need to be able to explain how ammonia and nitric acid are used to make fertilizers. You might be thinking, I'm not really sure about that one, that's phrased slightly in a complicated way, but really it's just they're used in neutralization reactions to produce soluble salts. So if you're asked how ammonia and nitric acid are used to make fertilizers, the explanation is just that they can then be used in neutralization reactions to produce soluble nitrogen containing salts, which can be used to make fertilizers. Okay, so once again, thanks for listening. It's been quite a lot this week, so I hope you've found this okay. Please message me if you have any questions. We'll do some starter questions on fertilizers in the next week's work. But if you think you need some more practice, or if you just want a little go at a test, try the wee test on BBC Bite Size or on Scholar for this topic. Okay, thank you for listening.